Algebra of limits will not alone do. So algebra of limits is like the technology, but you don't have the parts. Like you don't have knowledge out there. So to apply this technology, you need to test it out, right? So for example, so that's where the whole population of known limits comes up. This is where you have to make a cheat sheets. And then you apply this algebra of limits technology, these theorems, to find new limits. So
Hello, guys. Welcome to Cheenta School of Statistics and Data Science. We are a team of extremely passionate teachers, researchers, and statisticians from the top universities of India and USA.
so we need to know some really good. So it's similar to the limits of it's similar to the exactly the limits of all the whatever you have done in your classes. So for example, limit of n tends to infinity. Okay, 1 by n to the power any k is equal to 0, where k is greater than 1, right? This is one basic limit. Let me check the list out there if I have something. This is one such thing. Okay. Limit n tends to infinity mod of an, or like a to the power n is equal to 0 if mod a is less than 1, is equal to infinity, is equal to 1 if a is equal to 1, is equal to infinity if a is greater than 1. What will happen if a is equal to 1 and a is equal to a is equal to minus 1 and a is greater than, less than minus 1? So whatever a is less than, like a if a is less than 1 or minus 1, both of them it will neither converge, like limit doesn't exist. Okay, because for this it will be oscillating between 1 and minus 1, like 1 minus 1 1 minus 1, and for this case it will be like this, like it will be oscillating to, like one will go to one branch will go to infinity, one branch will go to minus infinity, and we will see what do we mean by one branch. These are called subsequence. We will learn in the next classes, and we'll see that this lim sup of this lim sup is nothing but the subsequence sub behavior of the sequence that is going, the maximum possible sub behavior sequence, subsequence behavior limit, and lim infinity is the maximum, the minimum possible subsequence behavior, that is limit. Like that is what lim sub and lim inf does. So therefore we'll see that this also oscillates like this. So what I will do now is I will check all the possible useful important uh, corresponding results in sequences. So essentially it's nothing but you use all the x is equal to infinity, use all x is equal to infinity, x tends to infinity of any f of x, all these results. For example, some results are like this: limit x tends to infinity, x to the power a, or a to the power x, sorry, minus 1 by x is equal to log of a if a is greater than 0. Okay, so similar like this, for in place of x you replace n. Okay, and you will get the results, it will be log of a. So there are lots of results. Like another important result is limit n tends to infinity 1 plus 1 by n whole to the power n, or 1 by x 1 plus x by n whole to the power n is nothing but e to the power x. Okay, so there are lots of results like this. Limit n tends to infinity log 1 plus n by n is nothing but 0. Okay, so these are certain things you should be knowing, and this is very important stuff. Okay, so there are lots of also other results, like lots of n to the power 1 by n. You know it's 1, right? You know it's 1. We have not shown it's 1, but it's like we can prove it, it's 1. Okay, and we'll show it probably today that it's 1. Okay, so let's do this proof that so this okay, let's not do this. I will tell you why it's okay. Let's try to do this proof. So n to the power 1 by n, let's say fn equal to n to the power 1 by n. So similarly, your goal is assignment is make a list of all such limits, and that is very important. The more you make, the more you can understand the relationships. Okay, and this is very important job. Okay, so the more you make, the more it's easier for you to learn. There are lots of like tan trigonometric stuff and all of this new stuff, and you will get this more clear when you do the limit of functions in the next module, like next to next module in limit of functions. Okay, you can also use that. Yeah, this will be more clear about on in that case. Great, but make a list of this. This is very important. This is very important, because you understand you can apply those to find complex relationships here. Okay, whatever complex relationship is given. Okay, if the, let's say these two are added, then you can add this up. Okay, or something like that, so you understand. So this is a very important thing. So if you take n to the power 1 by n, the basic idea is that step number 1 is that show fn is decreasing after n is greater than equal to 3, and since it's decreasing, so and show that fn is greater than equal to 1 for n greater than equal to 3, or you know that fn is greater than 0. You can understand from here. So therefore, the basic idea, okay, if n is greater than equal to 1 because n is greater than equal to 1. So the graph of this picture will be like this. So how to draw this graph? We will have a graph drawing, curve drawing session in when we do. So essentially, you understand to understand limits, you also need to know functions well. That's why differential calculus comes to a very big role in playing here to understand how the behavior of functions is. So to solve this part, so understand to solve problems of this functional form, you not only need but you also need differential calculus to understand behavior of functions. Okay, so let's try to do some problems. So this is something you will be doing, and so now if since f is decreasing after n and f is bounded, so you can use modern bounded theorem, which will be taught in the next class to show that it has a limit, right? Now you use now you can use those basic results that yeah, it has a limit, and you can use an epsilon delta definition to prove it, or you can use the functional form to prove it, L'Hopital rule. Okay, you can use L'Hopital rule to prove it too. So we will learn this discrete form of L'Hopital too. But let's do some past year problem. We'll explain these things, but let's do some problem solving based on these ideas. Okay, let me check the past year papers. Problem number 3 probably. No, not problem number 3. Okay, so if you check JAM 2018 problem number 2, it's asking that limit n tends to infinity 1 plus 2 by n whole to the power n square into e to the power minus 2n. Okay. So now you understand like so I will tell you how to do it. Okay, and how we use the the limit behave like the limit algebra of limits to solve this problem. So can any ideas out there how to solve it, guys? Yes, no, maybe. So understand. So one important result is this, that 1 plus x by n whole to the power n. You already knew that it goes to e to the power x, right? You already know that it goes to e to the power x. I have already told you here. How to prove it? It can be a different video, but I'm just telling you this is the standard formats. Okay, this is you have to know this and know the proofs of this. I'm not going to do this. So if you assume this, and let's say there's another an, which an is going to infinity, you know that. So then this will go to e to the power x whole to the power. So understand, you can write this as 1 plus x by n whole to the power n times, that is whole to the power an by n, right? So this will go to e to the power x, you understand. So therefore this will go to, you can see e to the power x times limit an by n, you understand. This is the basic idea, right? So in general, you can write this as, instead of an, you can do bn. So 1 plus x, or you can just do 1 plus 1 by bn whole to the power n, where an and bn both go to infinity. You can see that it's nothing but 1 plus 1 by bn whole to the power bn. This goes to e to the power 1 whole to the power an by bn. So therefore this must go to, this goes to e to the power 1. So therefore this must go to limit n tends to infinity an by bn. Got it? So therefore, in some sense, this will go to what? E to the power, so if it applies a general thing, 1 plus 2 by n square, 2 by n, kya tha? Yeah. So here, what is an and what is bn? Can someone tell me? What is an and what is bn?
An is n and bn is n squared.
No. Bn is n.
Maybe, sorry, bn is n and an is n squared.
N is n square, but bn is not n. Check the format, it's 2 here.
2 by n.
Yeah, n by 2. So it will be going like this. That's why also it includes a case of this. Why? Where here you will take bn is equal to n by x. X is a constant, right? So it also takes a general case. This in this case, so therefore this will go to e to the power limit n tends to infinity an by bn, that is n square by, so this, which is nothing but, you can also take like limit n tends to infinity e to the power twice n. Did you understand, guys? Twice n. So this is in some sense, in the limiting sense, this is going to e to the power 2n, and this is already going to e to the power minus 2n, which is 0. So therefore this will together go to 1. Do you understand this, guys? There's a multiplicative thing going on. The issue is that here it's going to infinity, here it's going to 0. So infinity times 0, okay, you cannot apply the multiplicative rule, right? This is the basic issue. So that's why we will learn something as something called big O notation. So the basic idea is this. The initial part is, in the long-term behavior, it's behaving like e to the power 2n. And e to the power minus 2n in the long-term behavior is also behaving like e to the power minus 2n. So their product in the long-term behavior will also behave like 1. You understand the basic idea? We'll see the big O notation coming into play here, and essentially it helps you. So understand, this case cannot be solved if you do it using the algebra of limits. Why? Because it's infinity times 0. So algebra limits only exist where a and b are finite. Okay. So when it's 0, it will not happen. So that's a problem. Also, you can do it in a different way. You can do it using something called expansion of functions. You can expand these functions and do it. That's also one possible way. But yeah, that's also one possible way.
If you're enjoying the video, show some love by liking the video and subscribing to the channel. We welcome you again to this passionate community of budding statisticians and data scientists. Let's enjoy the rest of the video. Stay tuned and stay blessed.